Assalamualaikum students. Students, today we are going to do giant molecules, right? And maybe we do ionic too, right? So giant molecules. You know what are giant molecules? When there is covalent bonding, you must know. When there is covalent bond, there are two types of structures. Simple molecules and giant molecules. In simple molecule, there is covalent plus intermolecular forces. When the covalent bond break or form, there would be a chemical change. And these intermolecular forces are linked to what? Physical. In giant molecule, there is network of strong covalent bonds. Covalent. Therefore, their physical and chemical both are linked to what? Covalent bonds, right? Now coming to giant molecule. All the giant molecules have network of strong covalent bond. The first one is what? Diamond. Huh? Diamond is what? Carbon. Diamond is what? Carbon. Each carbon is bonded to how many other carbon? 4. Each carbon to how many other carbon? 4. Each carbon to how many other carbon? 4. 4. It's tetrahedral, 109.5. Each carbon is bonded to how many other carbon? 4. Right? Each carbon to 4, tetrahedral, 109 angles. So, each carbon is bonded to 4 other carbon atom in tetrahedral geometry. Don't conduct electricity, no delocalized electron. In the carbon, in the last shell, there are 4 electrons and they're all involved in bonding. And they have network of covalent bond. This is the hardest substance due to the strong covalent bonds. That's it. What about graphite? You need graphite. Each carbon is bonded to how many other carbon? 3. Trigonal planar, 120 angles. 120 angles, right? This is a layer, planar. This is a layer, planar, another layer. So inside the layer, each carbon is bonded to 3 other carbon. Each carbon is bonded to 3 other carbon. They are making hexagon. Between the layers, there are weak ID forces. When each carbon is bonded to, look, this is carbon. When carbon is making 3 bonds, so one is unbonded, this becomes the delocalized electron. Like each carbon has one delocalized, so there is a sea of delocalized electron that conduct electricity. So graphite is a conductor of electricity. And between layers, there are weak forces. These forces can break. The layers can slide over each other. Therefore, graphite is slippery. It has layer structure. Inside the layer, inside the layer, each carbon is making 3 other bonds with the 3 other carbon. In trigonal planar geometry, in the layer there are delocalized electrons that can move freely, make it good conductor of electricity. Between the layer are weak forces, therefore the layers can slide over each other if external force is applied. Therefore, graphite is slippery. High melting point because there is network of covalent bonds. Coming to SiO2. You know, silicon is in group 4. So it will make how many bonds? 4. Oxygen is in group 6. It will make how many bonds? 2. So each oxygen is bonded to 2 silicon. Each silicon is bonded to 1, 2, 3, 4. Look, each silicon, 1 bond, 2 bond, 3 bond, 4 oxygen. Huh? Each silicon atom bonded to 4 oxygen atom and each oxygen atom bonded to silicon. This network of covalent bond. Hard high melting does not conduct electricity. That's it. But what you are supposed to know very clearly, each silicon is bonded to how many oxygen? 4. And each oxygen is bonded to how many silicon? 2. No delocalized electron. Network of strong covalent bond. High melting and high boiling point. Clear? Now, so when the bonding is covalent, there is possibility of what? Giant molecules and simple molecule. Both have covalent bonds, but in these there are intermolecular forces in addition to covalent. Both have covalent. And covalent is electrostatic forces of attraction between shared electron and the nuclei of bonded atom. When they attract each other, they get very close. The bond length is small. But the size of atom is also small. Smaller atoms make stronger bonds. So your next topic is what? Strength of covalent bond. Covalent bond in giant or in simple. What like when it is covalent, the strength of covalent depends on what? Bond length, which is the distance between the nuclei of two bonded atoms. This bond length depends on what? Size of atom. Huh? Now, if if the atoms are big, the bond length would be large. If they are small, the bond length is small. The nuclear attraction is more for the shared electron. It needs more energy to break. So bond length depends on what? Size of atom. And we know that down the group size increase, across a period size decrease. When the size increase, the bond length increase, bond length decrease across a period. Smaller atoms make stronger covalent bond as the bond length is small and the bond strength is more and the bond energy is very large. Down the group, if you see hydrogen halides, this is a highly repeated question. What happens down the group? What is the thermal, like they talk about the thermal stability. So this is more stable to heat. This is less stable. It breaks very easily. This HI break very easily. When HI break, keep in mind, it will result in the formation of iodine. So you will see purple vapors. In this, we don't get green gas. Why? It's not breaking. Why? Why it is not breaking? Because the bond length is small. The size of chlorine is small. Down the group, the chlorine increase, the size of the halogen increase. As a result, the bond length is more, the bond strength is less, the bond energy is less. Therefore, they're becoming what? Less stable to heat. This one is more stable to heat. This one is less stable to heat. It will not break easily. Next topic, ionic bond. So in covalent, the strength of covalent depend on the size of atom, that which atoms are overlapping. If there are smaller atoms, they will make stronger bonds. Now your next topic is what? Ionic bonding. What is ionic bond? Electrostatic forces of attraction between opposite charge ions. If there are two elements, if their electronegativity difference is more than 1.7, they are going to make ionic bond, and the larger electronegativity difference would be between metal and non-metal. Metal lose electron, non-metal gain electron. So they are cations and anions. Huh? Metal lose electron, they make cation. Non-metal gain electron, they make anion. These cation and anion arrange themselves in such a three-dimensional lattice. Cations and anions arrange themselves in regular alternating arrangement called giant ionic lattice. Huh? If you see this positive ion in this whole big lattice, this positive is bonded to how much anion? 1, 2, 3, 4, 5, 6. So this is bonded to 6 anion. And if you look at this one, now look at this one. Wait. Positive is bonded to 6 anion. If I take this anion, huh? This one is not very clear. Wait, let me check. Bonded to 1, 2, 3, 4, 5, and there is another. Look, each anion is bonded to 6 cation, and each cation to 6 anion. Look at this. Cation bonded to 1, 2, 3, 4, 5, 6, and each anion 1, 2, 3, 4, 5, 6. This is called coordination number. It's a giant ionic lattice. The cation and the anion arrange themselves in regular alternating arrangement. The ions are regularly arranged. Huh? Each cation is bonded to 6 anion and each anion to 6 cation. All ionic compounds are hard crystalline solid, high melting. They don't conduct in solid. The ions are fixed. They're not moving freely. They just vibrate. And but when you put them in water or melted, the ions become free to move. Now, this is like what? How many aluminium? 2 aluminium. I'm drawing aluminium oxide. So there are 2 aluminium, there are 3 oxygen. It's what? 13. 283, 283. This is 26, 26, 26. So each will lose 3 electron. 3 electron become 3 plus. After losing 3, how much are left to 8? 3 plus. So total electron lost are how much? 6 out of 6. 2 are given to one, to another, to another. Huh? The last shell is now complete. So how many oxygen? 3, and how many aluminium? 2. They both lose 6. They all gain 6. Clear? Next, strength of ionic bond. You know, smaller atom makes stronger bond. So ionic bond strength depend on charge of the ion and size of the ion. Look, charge of the ion plus minus 2 plus 2 minus 2. Is there any difference between oxide? No. Cambridge is not going to give you two quite different situations. Like you might be thinking that they can ask you to compare sodium oxide with magnesium, huh? Magnesium nitride, huh? Not possible. Why? Neither metal is same nor non-metal. The question would be of very low level, right? So keep in mind, one thing would be same, like in this. What is same? It's same. The charge of the Mg is large than Na plus, and therefore when the charge is more, it attracts oxide more strongly. So ionic bond depends on what? Charge of the ion as well as size of the ion. Which ions? The ions should be, the charge should be more, the size is small. So strong ionic. Strong ionic bond is only possible when the size of the ion is small and the charge is small. Right? Now look at this one. This is a question from the past paper that describe the trend. Is there any difference in oxide? No, it's same, same, same. Where is the difference? It's plus 2, plus 2. So where is the difference? The size. Size is becoming larger. When the size is becoming larger, do you think beryllium will attract oxide more strongly or barium? Definitely beryllium. The ionic bond weaken. Ionic bond weaken. They need less energy to overcome. Now, metallic bond. But this metallic and the summary, this I'm going to do with you in the next lecture. In this, I think you understand that the oxide is same, the charge is also same, but the size increase. So barium 2 plus attract oxide very less attraction, so it's not very stronger bond. Like it is stronger, but not as strong as this. The size of barium is large, the attraction for oxide is small. I hope you understand. See you in the next lecture for metallic bond and complete revision of all type of bonds. And before leaving, don't forget to like and subscribe and share my channel. Okay, Allah Hafiz.